Okay, 2.2, Simplifying Radical Expressions, is our first lesson for this unit. So you're on our second last unit, which is kind of exciting. What we're looking at here is we've got radicals, which we looked at last year, and breaking them down and putting them together. For the purpose of this lesson, we're just going to be analyzing how multiplication kind of pulls them apart and puts them back together. And then we're going to get into how that can impact adding and subtracting and multiplying and dividing and all of that. So the key thing that we learned last year was that if we have two things multiplying underneath a radical, then we can actually pull those pieces apart. And so we can go back and forth between these two pieces. So when we look at 2 root 4, what we can actually think of that as the square root of 4 times the square root of 4. So keep bearing in mind the idea that 2 actually is the same thing as the square root of 4. And so those two pieces can be simplified or reverse constructed. If that's the case, then we can also write this as the square root of 16. This piece here is your mixed radical, and this piece here is your entire radical. In this particular case, because we're dealing with 16, it is a perfect square, so this could be simplified to be just 4. So the first example that we're really going to dig into is we're going to try and arrange these from greatest to least. So to do this, in the first case, in A, that's what it's referring to, we want either our radicals to be that are underneath the symbol, like the value under the radical, to either all be the same, and if they aren't all the same and we can't make them all the same, then the only other way we can compare them is to make them entire radicals, so that we've at least got everything all under there all at once, and then we're just really kind of just comparing whole numbers. So that's what we come across in A. So 5 root 2 is the equivalent of the square root of 25 times the square root of 2. 25 times 2 is going to be 50, and so I'm going to leave that one there. 2 root 5, on the other hand, is not the same thing. That's the root of 4 times the root of 5. And so that could be root of 20. So a little bit different just because of that radical and where the numbers are positioned. 4 root 3 is the last one. And what we're looking at here is going to be the root of 16 times the root of 3. And that gives us 48 under that radical symbol. Now we can compare these three values because they're all under the square root sign and they're all entire numbers. So 50 is going to be bigger than 48, which is going to be bigger than 20. So their radicals, when we take the square root of them, are actually also going to follow that same pattern. So we're asked from greatest to least. You also want to write them in the form that the question was originally asking. So 5 root 2 is greater than 4 root 3, which is greater than 2 root 5. Now I might not have gotten this answer if I had looked at them here, because I could have been like, well, 5, the square root of 5 is bigger than the square root of 2, but because I'm multiplying it by a bigger number, that's what then influences that value being larger. So that's when we have different radicals present. But for B, we actually have all the same radical, which is the cube root of 2. In this scenario, if we're dealing with everything being the same, we can compare them directly. So we've got 9 cube root 2's, 11 cube root 2's, and 8 cube root of 2. So when we look at it this way, because they're all multiplying by the same number, it would be the equivalent of saying, well, how does 9 times 3 compared to 11 times 3 compared to 8 times 3? Well, we could just look at what's multiplying to determine which one's going to be biggest. Same thing happens here. So again, when we have the same radical, we can look at the coefficient. So in this case, greatest to least, we've got 11, the cube root of 2 is greater than 9, the cube root of 2, which is greater than 8, cubed root of 2. Finally, and we're not going to come across this because as you saw on the cover page of your booklet, this unit is completely non-calculator. When we run into this scenario where we have different types of radicals, we've got a quartic, a square root, and a cubic root, there's no way of turning these into each other. We're not going to get into fractional exponents and common denominators. That's not where we're going with this. So instead, what we're going to do is we're just going to use our calculator. So you can go into your calculator to punch in the fourth root. You might need to punch in 4, and then there might be some sort of button that looks like something along those lines, maybe. If you can't find it, ask and I can help you out. Or you can Google it on, just search your calculator type and it should tell you the exact button because every calculator is a little different. Division properties of radicals are quite similar. Just like we had exponential laws, and when we were looking at multiplying exponents, we would add the or multiplying powers, we would add the exponent, and when we're dividing powers, we would subtract the exponent. Well, the same idea here is that we can break it apart, just like we did with multiplication. So if we're taking the root of any fraction, we can take the root of any part of that of both parts of that fraction. So some key things to note is that n is this index out in front, and so we already have seen that kind of changing up here. Okay, and then n is looking for perfect squares. When it's 2, n equals 3 means we're looking for perfect cubes. You want to know your perfect squares for probably the numbers 1 to 20 would be good, at least 1 to 15. Those are going to be your handy ones. For your perfect cubes, I would say 1 to 5 is sufficient. So they're cubes. And that will help you when we get to here. And one other point I should point out, and it kind of ties in with this, is that whenever we talk about perfect squares, remember it's a number times, and I'll use a letter other than n, a times a. It's a number times itself. So when we're dealing with negative values, it's a negative times a negative. When we have two like things multiplying together, we end up with a positive. For cubes, we've got a number times itself again, which means we've got 3 negatives multiplying together. So a negative times a negative is a positive, but a positive times a negative is a negative, which means that we are now dealing with a scenario where we are allowed to have negatives in some of our perfect values. In general, we say that even numbers, even roots can't be negative, and odd ones can be. So we look at example 2, and we say, okay, well, the cube root of all of this. Well, the first thing I'm going to know is I can take out that negative. So I'm going to bring that on out in front. The next thing I'm going to do is look for perfect cubes. It just so happens that 8 is a perfect cube. And then we're going to have to maybe see if we can figure out the perfect cube of 135. So either you know the perfect cube that's going to go into that, or if you're really stuck and you're like, Miss Conrad, I just can't remember. Last year you learned about prime factorization, and we can figure it out from there. So we do this by breaking it into its pieces. So 5 can go into this, and you would figure that out. 27 times, and then we've got 3 times 9, that's 3 times 3. Or you might recognize right here that 27 is a perfect cube. So we can break it apart from there. So we're using both our multiplication principles and our division principles here. So I've taken the negative out of my radical. Now I've got the cube root of 8, the cube root of 2, the cube root of 27, and the cube root of 5. So using both division in terms of numerators separate from denominators, but also that multiplication piece where I can take the radical of both. From here, the cube root of 8 is 2, cube root of 27 is 3. And I can stick these both back underneath one radical symbol instead of having to write it twice, because 2 and 5 are both not perfect cubes. So that would be my final answer. When possible, we want to take that negative out of the radical, so that's why that's brought out there. In this scenario, the first thing I'm going to notice is what it's asking me for. I want an entire radical. The second thing I'm going to notice is that it's an even index, which means if I try and put that negative underneath, it's going to disappear. And I can't change signs partway through a question if I'm just trying to simplify it. So I'm going to leave that negative out in front. The fourth root of something that equals 3. Well, I know 27 is a perfect cube. It's 3 cubed. So what I'm looking for is actually 3 to the 4. Now you could leave it as 3 to the 4. That's an option. Or you can write it as 81. 27 times 3. Okay. So I'm going to write it as 3 to the 4. Now the reason that I'm going to do that is that it's multiplying by 2 times 27. Well, 27 is actually 3 to the 3, and I'm going to be able to simplify this. Because when I'm dividing by a power, I subtract the exponents. So I've got 2, or 3 remaining in the numerator, times 2, or I could write that as 4, the fourth root of 6. But that negative stays out front. Don't lose your negative. When we look at all of this, the key thing you need to note is we want to always be able to put things back in under our radical, but in the end, we want to simplify it. We don't want things to be complicated if they don't have to be, and that's been something that we wanted to see all throughout our math course so far. It's what we're going to continue to look for in our last unit. And so always try and cancel where we can. For example, those 3's. Now, the next example asks, for which of the which values of the variable, is each radical defined? So radicals with an even index, and this is what we talked about higher up on the page, even index are not defined when it's negative. That means that any time we have an even index, and remember if we don't write it, it's implied that it's 2, that this whole thing has to be bigger than or equal to 0. Negative is less than 0, remember. So when I look at this and I have to determine where my variable is defined, I can take my entire piece under the radical and I'm going to set up an inequality. So 27x squared has to be bigger than or equal to 0. Once I've got my inequality written, what I'm going to do is I'm going to try and isolate my variables. So I've got x squared has to be bigger than or equal to 0. And then I can take the square root of both sides. Well, the square root of 0 is still 0, so x has to be bigger than or equal to 0. Now, usually when we introduce that square root, if you remember from our quadratic unit, we would have to insert that plus or minus in front of it, so it would be plus or minus 0. But because 0 is actually not one way or the other, it's not positive or negative, we don't need to include that. For part B, same thing. We're going to say, okay, well, this whole chunk, we see that negative under there and we're like, what the heck? Like, we can't have negatives under there. But remember, there's a variable as well, so we can maybe play around with that to make it so that this is possible. So again, we say it's greater than or equal to 0. If you don't believe me, try plugging it into your calculator. Take a second right now, grab your calculator, and try taking the square root of -9. And if your calculator doesn't give you an error message, then something's wrong with your calculator. We can have that conversation in class. So again, I need to move that 12 onto the other side. So I need x cubed. Now, if you recall, when we divide by a negative number, what needs to happen is that, we need to actually switch the direction of our inequality. So it becomes, so when we flip that sign, our cube now needs to be less than 0. So now we know that x cubed needs to be less than 0 in order for this to be true. And so x then is going to have to be less than 0. And again, you can do the cube root piece, but the cube root of 0 is still 0. So that, in both of these cases, defines my radical. So when if I was given this equation and I was asked to simplify it, what I would have to do is look at it and say, okay, well, that actually becomes 9 goes into 27 3 times, so that's a perfect square. I'm going to take that out. I've got 3. X squared is also a perfect square, so I can take that out. But I would still have to go back to my original equation and say that x had to be greater than or equal to 0. So example 4 is our last one. We've got a couple parts to it. So it asks for the values of our variable that define our radical, and then we have to simplify. So just like kind of what I tacked on to the end of the previous example. So part 1 is just figuring out what's allowed. It's to be bigger than or equal to 0. So from here, I'm going to take it and go divide by 45, which doesn't change anything. So a squared has to be bigger than or equal to 0. So a has to be bigger than or equal to 0. So that is my values where my radical is defined. If I look at 45, I'm looking for possible perfect squares that go into it. 9 actually goes into 45 as well. So stepwise, if I was doing this, 9 times 5 is what gives me 45. I've also got a squared, which is a perfect square. So if you like to circle them to help you remember that they're perfect squares, go ahead and do that or identify them. Square root of 9 is 3. The square root of a squared is a. and we're left with 5 under my radical. So that's my simplified version. In our next one, it's an even index, so I am going to have that restricted domain. So 7z must be bigger than or equal to 0. So z must also be bigger than or equal to 0. And that's part 1. Part 2, as I'm going to see, is 7 a perfect quartic? Absolutely not. 1 to the power of 4 is 1, so that's great. It's less than that. But my next one is 2, and 2 to the power of 4 is actually 16. So there's no whole number that's going to give me 7, so it's not a perfect quartic. And z is to the power of 1, so it also can't. You can't take the 4th root of it. So we're done here. It's as simple as it goes. Our last one is a cubic. Remember that odd index values actually can be negative. Therefore, we have no restricted domain. I'm looking for a perfect cube that goes into 24, and that will be 8. If I want to use 8, I need to consider what it multiplies by, which is 3. Remember to keep your index there, don't drop it. Y to the 5 also has a perfect cube within it, remembering that power law that I mentioned earlier, where anything to the power of any power with a common base, we add the exponents. So vice versa, we can break them down. Here, that means the cube root of 8, which is 2. Cube root of 3, I can't do. So if you want to circle your perfect cubes. The cube root of y cubed is just y. So we're left with 3y squared underneath, and that would be my simplification. So you got lots of practice questions in the workbook. Go ahead and give those a try, and then you're ready to move on to the next lesson.